Hi guys, so we'll be talking about the binary adder. So what is binary adder? A binary adder is a digital circuit that performs the arithmetic sum of two binary numbers, provided with any length. A binary adder is constructed using full adder circuits connected in series, with the output carry from one full adder connected to the input carry of the next full adder. So, as you can see dito sa screen natin guys, we have the half adder. Madali lang siya guys kasi addition lang. So, let's say for example, A is 1 and B is 0. So, if you add that, the sum will be
0,
and the carry is
1,
so that's the idea of the half adder. So, next is the full adder. Since our carry here in the half adder is 0, we will have to carry in that sa full adder. Since the binary adder is an arithmetic sum of two binary numbers. So yung carry natin dito sa half adder, dito sa full adder is still 0. So assuming A and B, A is 1 and B is 0. So if you add A plus B, the sum is
1,
A plus B plus C. C in. So the sum is
1,
at the same time yung carry niya 0 pa din. Kasi nga 0, 0 plus 1. So ang next is the truth table. So we will now generate the truth table sa binary adder. So let's start with the half adder. So if 0 is 0, 0 plus 0, the sum is 0. And the carry is 0. So if 0 plus 1, the sum is 1 and the carry is 0. Same with if you add 1 plus 0, the sum is 1 and the carry is 0. So if 1 plus 1, the answer here for sum is actually 0, the carry is 1. So let me explain, I will explain that. So when adding, usually if you add 1 plus 1, the answer is 2. So since we're dealing with binary adder, we can't do that. So you can't put 2 here. So this is wrong. So what we will do, since we're doing binary adder, the idea there that the sum is 0 and the carry is 1 is, let's say 3 plus 9. The answer there is 12. So what happens? We carry out 1. But the idea here sa binary adder, we only get the base number, which is 1. So what will happen? The 2 will be 0. Kasi yung carry niya is 1. Basically, we only get the base number. So what happens is, if you add 1 plus 1, since you will carry this, 1 plus 1, you will carry 1, and then the answer here is 0. So, ganun lang guys. So guys, going back, the sum is usually is A X or B, and the carry is A and B. So let's continue sa full adder circuit. this time we have the carry in. So to get the sum, madali lang siya guys, i-add lang natin. So if 0 plus 0 is 0 plus 0, so the sum is 0 and the carry is still 0. So if 0 plus 0 is 0 and plus 1, the sum will now be 1 and the carry is 0. So ganun lang gawin natin guys. So 0 plus 1. So the sum is 1 plus 0. So it's 1 here and the carry is 0. So let's say here 0 plus 1 is 1 plus 1. So same thing guys, the rule of addition when carrying dito sa binary adder. So the sum will be 0 and the carry will be 1. So dito the sum is 1, carry 0. So the sum is 0, carry 1, 0, carry 1. Okay, let's see. Let's say, let's see. Tatlo siya. So 1 plus 1 is, the sum is 0. And the carry is 1 plus 1. So what happens? Ang sum natin, magiging 1 na siya. And then the carry is 1. Still 1. So ganun lang siya guys. Next is the diagram.
So now that we have already derived the truth table for the basic half adder, we will now proceed into making the combinational logic diagram of the half adder. So given the truth table, it is stated that there is an XOR for input 1 and input 2, and for the sum and the carry is an AND gate. So here, if we will tick the values for input 1, 1 plus 0, our sum is 1, and if we will add 1 and 1, our carry is now 1 and our sum is 0. So next we'll proceed with the full adder. So earlier from the half adder theory, we only have two inputs in which we will have a sum and a carry. On the other hand, the full adder makes use of three inputs, namely what we named here operand 1, operand 2, and the carry in. So this is the combinational logic diagram of the full adder, only for the full adder with 1 bit inputs. So if we will add 1 plus 0 and 0, our sum is 1. And if we add 1 plus 1 plus 0, our carry out now is 1 with sum 0. And if we will add 1 1 1, we should have 1 1 as the sum. So this representation basically means that 1 plus 1 plus 1, if we will convert it to to decimal, we will have value 3, and our sum, or the output that we have here, shows that we have the value 3. So why is it that stated that this is only applicable for 1 bit? It's because if we want to further the addition of the binary values, we should add, if for example, if we want to add two 2-bit numbers, we should instead separate these bits, separate this for every bit. We should have a separate input in which it will be made like operand 1, operand 2, operand 3, operand 4 with the carry in, which will also change the number of bits for the sum and the carry out. So in Logisim, we can simply make this the half adder. We can simply make the half adder by going to the to the gate, to the arithmetic, and then we put adder. And if we want to make a half adder, we should simply just input, we should only have two inputs. For example, this input 1 and input 2, which the lower part here will produce the carry and the upper part will produce the, and the linear middle ng 2 and 1 will have the sum. So as earlier, if we will add 1 and 0, we should have 0, 1. 1 for sum, 0 for carry, and we will try to validate that with our half adder theory here. So 1 plus 0 is sum 1, carry 0, and as you can see that they have the same values. On the other hand, if we will add 1 and 1, we should have carry 1, sum 0, and carry 1, sum 0. On the other hand, we have the full adder. The full adder. The full adder is just, we can make it in logisim similarly with the half adder, but now we have three input values, what in which we name the operand 1, operand 2, and the bit carried in. And the bit carried out is the, if there is bit carried out, it should proceed with the carry out, and sum is only for two input value, sum and also the sum. So here, if we will add 1 and 0 and 0, we should have sum 1, and we will try to validate it with our logic diagram for the full adder theory. So 1 plus 0 and 0, we have sum 1, carry out 0. And as you can see, they have the same value. Sum is 1, carry out is 0. On the other hand, if we will add 1, 1 plus 0, we will now have carry out of 1 and a sum of 0. And if we will add these three single bit ones, we will have 1, 1, which represents the decimal value 3. Now we will proceed with taking the Boolean expression for the full adder diagram. So we have labeled the three inputs because the full adder receives three inputs. Now we have labeled this as A, B, and C. And the carry out we labeled as F2, and the sum we labeled as F1. So we can take the Boolean expression for this F2 and F1 by analyzing, using the logisim and analyze the circuit. Now this is the values represented in the truth table, which comes out. We can also, and these are the, for F1 or the sum, we have this Boolean expression. This Boolean expression, a prime b prime c plus a prime b c prime plus a b prime c prime plus a b c. That is for our sum. And on the other hand, if we want to take the Boolean expression for F2, we will have bc plus ac, bc or ac or ab. So that is how we can take the Boolean expression for this logic diagram. But we can also do this one by one by taking all the expressions that will be the result of every two inputs that passes the logic, each logic gate, which we will have 1, 2, 3, 4, and 5 4 expressions rather. 1, 2, 3. We will have 3 expressions rather before we will reach the final F1 and F2. So we can do this by um, simply putting outputs. We'll have output, we'll have q. Label this q for here, and the sum we already have it, so we will proceed with this second output. Label is w, and lastly this one. Now we have three expressions, we'll label it as e. So in order to take this, the Boolean expression for every expression before reaching the f1 and f2, we'll just simply analyze the circuit. And now we have the truth table. This represents the truth table for the expressions q, e, f1, f2, and w. And the Boolean expression for q, we have ab plus a prime b, or a b prime. And for e, we have a prime bc, or a b prime c. And for w, we have ab. And if we want, so now we have already derived the Boolean expression for all of the possible outcomes, which we labeled QWE, and also the Boolean expression for the sum and for the F2. Now we will proceed into taking the Boolean expression of the half adder. Adder theory. So here we should simply just label this as A. We should change this. Should label these values, these outputs, we label this as Q, and the sum we label as W. The input 1 we label as A, and the input 2 we label as B. Now we just simply need to analyze the circuit, and the truth table will be derived for us, and the Boolean expression for the sum is Q. For Q, or the carry, we have AB, is simply an AND gate, and also for the W, we simply can represent this A prime B plus A B prime into an XOR gate. A XOR B, that is if we use an XOR gate. So that would be it. That is how we derive the Boolean expression, the truth table, for the binary adder, for the half adder and the full adder. As a recap, we will have, for half adder, we only receive two inputs. Respectively, our input is should have in if we should have outputs sum and carry, and for the full adder, we have also outputs sum and the carry out, which the full adder only receives 3 inputs. So that would be it, and thank you.